So if you have started interactively, you have to wait until that cell completes before you can go to the next cell of the workflow. If you have sent it to the background in the way that I was doing it, we can keep going to the next step. Any questions so far? Is someone completely lost? Is someone running things on Fugaku? No? You're all using the laptop, the notebook? Yeah? Yes, I need to use the microphone. Yes. Okay. Has anyone running things, do you all have the TPU, or do you have to use the CPU, some of you? Or you were all faster than me and then you use all the TPU nodes and then have to stick to CPU, I guess. So we have pre-calculated runs in the runs directory, so we could already look at the content. So while we are waiting for things to finish, again, we don't need to wait for things to finish to proceed with the tutorial. But if everything runs, this is the content of the directory that you should see. So our workflow had 11 steps. These are the 11 modules that we define in it. So there will be one directory per module. There is an analysis directory which will combine all the Capri eval steps. The data directory contains your input data. So basically the run contains all the input data as well. So the run is an archive of what you have been doing. So it contains the restraints and the log and the PDB files. There is a log file which tells you, well, you can look, if you look in this log file, you will see how much time did it take to run that particular workflow. Topar directory contains topology information and force field information. And the last one is a traceback directory, which basically allow you to follow a model at the end, say model number 1 at the end of your workflow. You could follow where was it in the other steps. You know, it could be that model 1 at the end was model 100 at the beginning, or things like that. So you can see how consistent does the model score in all the stages. So while things are running, so if you want to know, which models and where to find information about the scores and the rankings, so the important files are human readable files, and important files are found in each Capri eval module. So this is why you want to add those modules in your workflow so that you extract the statistics. Even if you have no reference structure, it doesn't matter, you want to get those. This is the content. So step number 10 in our workflow was the Capri evaluation, basically the statistics and the analysis of the clusters that have been generated. Okay, and when we have a cluster, the scores are calculated on the top 4 model of each cluster. So we have the same number of models that contribute to the score. And you see the first lines of this file. So there will be 1 line per cluster. So you see the clusters, and so Capri SS is for single structure, and there is also a file called Capri CTL for cluster. So you see here model number 1, 2, 3. You were referring to the third model is maybe better, but so they are there. 1, 2, 3, and then their rank is here. The score. So this is this HADDOCK score. This simple scoring function I described. So this is not a binding energy. It's just a score. And then since we provided the metrics, the reference structure, it's giving you how far is this model from the reference. The first column here is if you look at, which column is that, that's the interface RMSD. So that's the RMSD compared to the reference calculated on the interface residue of the complex. So you see the first model was 1.35, so it's quite good. So that's in Capri, 1 angstrom here will be high quality, 2 angstrom, up to 2 angstrom will be medium, so we are 1.3. Model number 3 is slightly better. Again, our scoring function is not perfect, but it's quite okay. And then this is the fraction of contact that are correctly reproduced. So even if the RMSD of the first model is slightly higher than model 3, the contact it makes are better. You see it has 86% of the contact that you find in the crystal structure of the complex, the reference are reproduced. While this one has a slightly better backbone RMSD, this is backbone RMSD, but the contacts were slightly lower. And then there are other metrics, and if you scroll, you will also find in there, so these are all different Capri metrics. Then you start seeing the restraint energy, how well does it satisfy the data, angle energy, bond energy, buried surface area, so the area of the complex, how much of the surface is buried between the molecule, over restraint energy term, and you get also the van der Waals electrostatic. So everything is basically listed here. So this is, I think, the electrostatic, and this is the van der Waals energies. So you can find all those. And here you have the explanation that I just gave you, basically. Okay. If you call Capri after like a rigid body or flexible refinement, you will only get this file, which is Capri SS, which is a single model analysis. If you call the module after a clustering step, you will start getting a second file, which is indicated here. You see it as Capri underscore CLT, and this is now the statistics per cluster. So it's the average plus standard deviation calculated on the core model of each cluster. So now this file has more column because you get score, HADDOCK score, standard deviation. And it will have much less lines because the number of lines will be equal to the number of clusters. So you see in this case, the first cluster, which was rank number 1, has the best HADDOCK score, minus 120, plus minus 7. The second ranked is minus 98, plus minus 8. And you see that those two, if you consider the standard deviations, do not overlap. Okay, so you will say that the first cluster is significantly better than the second. And if you look at the interface RMSD, you also see that the first cluster corresponds to correct solution in this case because we have the answer. While this 1.5, it's not an acceptable solution, but it's a bit off. And the last one is at 10. That's a very different solution. Let's see where my run is. So it's still doing rigid body. I hope that more of you have finished. Again, if you are running iteratively, you have to wait for it to finish before you can go to the next step. Oops. Okay, so this is what I've been explaining you. Cluster statistics. So I told you that HADDOCK now is generating these HTML files that allow you to visualize the results. Okay, so if you look into the analysis directory, it contains all those. And you will see in the analysis directory a directory for each Capri step. So these are HTML files, so you can open them in a web browser, and they are interactive. So let's view the table. So this is now opening the table in the Jupyter notebooks. It's a bit different than opening it through a web browser. But this table now is for, there were only 3 clusters. Remember, we did a very limited sampling, 100 rigid body model, 20 refined model. So we have 3 clusters, and this is basically presenting you a more user-friendly visualization of the content of those files. And if you, in this case, you cannot order per column, but if you use the HTML version of that file, you can order the results per column. So if you're interested, I want to sort my results based on the van der Waals energy because I think it's very important, you can sort automatically those tables. I'm on my laptop now just looking at the same content here, and you see this is the content of this analysis 10 Capri eval, and you see all those files are also HTML files. So there is a report is the one that contains everything. So let's open this one. So the report is here. So this is the report, the cluster base, and you see here all the plots, basically, that are appearing. So these are interactive plots. So if I go somewhere on the model, I want to know what was this guy, it's telling me what the coordinates are in the plot, which is basically the RMSD from the reference versus score. It's telling you which model it is. So it's nice to visualize. And that's why when you run a workflow, you always want to have these plots, even if you don't have a reference, because at least you can visualize. You know, if your docking converges nicely, what you want to see, if it's really, really good, you might have only one cluster, and the scale here is very small because everything is close to 0. 0 will be your reference structure, the best model. If things converge well, you might have multiple clusters, but you want to see kind of an energy funnel where the best cluster is significantly better than all the others. If you have no convergence, you will see a potato of points, and then you have a problem because you cannot really make a distinction between clusters. So in this case, you see that let's remove my cursor. If you look just at this plot, we have 3 clusters, and you see that the first one is clearly better in that case. And the scale, so this is the score, but you also see different energy terms. So this is dissolvation, van der Waals, electrostatic, restraint energy. And then you have the same plot, but for DOC-Q, that's another metric which is used in Capri, ligand RMSD. And at the end, you also see the distribution of scores in the clusters, which is also interesting. And these are these box plots that tell you what is the distribution, where you see the median and the first and second, third quartile. So again, to visualize your docking run, these are very useful. So this is what I just demonstrated you, but within the browser on my laptop. But here you can also, in the Jupyter notebook, generate those plots. So it's using another library to generate those, but you get those plots here, and these are also interactive within the notebook. Okay, so that's nice. The distribution plots that I was showing you, they're also there, and again, you can get all the statistics just by going over those plots. So this is not specific to the notebook, okay? If you run a workflow and you have added Capri analysis, I think even if you don't add it, it will add it for the last step, if I'm correct. So you get that, okay? So you don't need to do anything, but you get those. Now, here there is just a simple script. So this is not part of HADDOCK. This is just to look at the results that we have now. And it's going to analyze the pre-calculated run to get some statistics. So this is a simple bash script, basically, that extracts some data. So it's looking at the different stage of the docking, just so that we can see, you know, how good or how badly was HADDOCK performing. So you see, we sample 100 models at the rigid body docking stage. And you see, based on Capri statistic, 19 out of 100 were of acceptable quality or better. Okay, it's about 20%, and the other 80% are basically wrong model. But that we can only do if you know the answer. So that's, you know, that's, in a real case, you will not have this information, but it's just to understand a bit. And out of these 19, one was below 1 angstrom already. So probably the input structure are quite good. There are no large conformational changes if we reach that. Then this stage is, actually this was 4 out of 10, so it looks like we were only sampling 10 models out of 20. In this particular run, because what we are running 20 models, and here it's only analyzing 10. So they are, when we make the selection from 100 to the top 10, we have 4 out of 10. So the scoring is working quite okay because our sampling was only 20% hit rate if you define an acceptable model as a hit. After scoring, we have a 40% hit rate. So we're enriching compared to random, which is, ideally you would like to have 100%, but okay, scoring is not perfect. And then you can see the value of RMSDs. For example, the best model that we had was 0.9, but this one, at the end of the workflow, this model that we have is 1.96. When you add flexibility, you are not always moving closer to your target. You might also move further away because you are shaking the system, okay? So sometimes you You hope to move in the right direction, but there is no guarantee of that. And if your starting point was very close to the right solution, by adding motion to the system, you are more likely to move slightly away from it. Just the thermal energy that you put in a system will just move you slightly further away than not. And the force field is not perfect, so there are many imperfections. But still, we are generating quite good models. There are some questions here. You know, how does the quality change of the best model after refinement? So this was actually the quality of the best model. If you look at here, in terms of RMSD, it's not really improved. If you look at the fraction of contact, the best model, so this one has a low RMSD, but the contact are less. This is very good already in terms of contact. You know, 0.67 is very good. The top ranking one, or the best one, was 0.82. After refinement, you see at the end of the workflow, we have 0.86. So it seems that the flexible refinement, at least in HADDOCK, is quite good at improving the contacts, even if the RMSD might not always improve. We have cases where you improve RMSD by 5 angstrom, which is a lot. But the more data and the more good data you have, the more likely it is that you're going to push the system toward the right solution. Is the best model always ranked first? No. And we see, for example, after rigid body, no flexible refinement, the best model is at position 18. After the final refinement, the best model is at position 3. And it's quite close to model 1. Well, best model is relative because it depends on the metric that you decide. You know, if DocQ is your metric, then the best model is actually at rank 1. So it depends a bit what you look. So if we think in RMSD, the best model might not be rank 1. But in each case, if you think of RMSD and contact, DocQ is a combination of the two, then the scoring is quite good. Okay, so what else do you get? So if you remember in the workflow, we had added one final module, which was the contact analysis module. And this generates 2 plots. It gives you a distance matrix where you can visualize what are the contact in your model. And it gives you these chord charts, which are quite nice. So you get this plot of your interaction. So the outer circle indicates the chains. So you could have this plot for if you do a trimer, the free molecule docking, you will see the outer circle will have 3 colors. Then the inner circle indicates the amino acids that are in contact. And they are color-coded based on the type of amino acid. And the chords between them are indicating the intermolecular contact between the chain. Okay, so you can visualize the complex in PyMol or whatever camera, what you prefer, VMD. But this is giving you a direct view. And the chords are also color-coded based on the type of interaction. You know, is it a apolar interaction? Is it a charge, positive, negative, 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 all of that. So it gives you a visual impression of your interface. And if you go, again, it's an interactive plot. So if you go somewhere, it's telling you this is arginine 98, and it has a total of 5 contacts with the other chain. So you can directly look in this plot and say, well, which residues seems to be very important because they make a lot of contacts. You know, these ones are interesting. Some of them make only 1 contact, like this one. The arginine, I went randomly on that one. You see it makes a lot of contacts. So that's probably a residue which is very important for the interaction. So this is also useful when you want to analyze your models and maybe select mutations. And if you go onto one of those chords, it's telling you what the contact is. Okay, so that's a nice interactive analysis of your results without having to do a visualization. And the other plot was the RMSD matrix. It's not in the notebook. And you see those plots are generated for each cluster, okay? So with cluster 1 to 3, so you can compare cluster. So what we looked at was the chord chart, but there is also this heat map, which we can visualize. And this is this kind of plots. Okay, so now you have sequence versus sequence. This is your first molecule. This is the second molecule. And these are all the intermolecular contact between those. You have looked at the structure. If you look at this 2D plot of distances, this protein contains alpha helices. Do you know how to recognize an alpha helix on such a plot? So here we are looking at short distances. If you have an alpha helix, what is a short distance? Your neighbors, that's the chemistry gives you your neighbors. But what is the next short distance that you find in an alpha helix? Well, if you take one turn, then there will be two residues that are close in space, okay? And one turn in an alpha helix, it's 3.4, whatever. So if you would have an alpha helix in this plot, you should see along the diagonal two lines that are parallel to the diagonal with a separation of 3 to 4 residue compared to the diagonal. So this will point to alpha helices. And I don't think that, we can visualize, but I don't think this system has alpha helices. We don't see this pattern. What we see are these lines that are perpendicular to the diagonal. And these are indicative of an anti-parallel beta sheet. So you have a beta sheet, a turn, another beta sheet. Okay, close to the turn, the distance separation is short, and then as you move along the beta sheet further away from the turn, the residue separation increases, and that gives you these perpendicular lines. And here and there you see a parallel line to the diagonal, and these are parallel beta sheets in your structure, because then if you are the beta sheets are walking in a parallel directions, as you move as you step on the ladder of the beta sheet, the difference between the residue numbers of those remain constant, and that gives you a parallel beta sheet. So that's just, when you look at those maps, you see the secondary structure. And again, this is an interactive map, so if I go somewhere on a point, it's going to tell you what it is, and it also gives you a contact probability, which tells you how often is this particular contact seen in the cluster. So if it's seen in all of them or not. So back to the notebook. So let's look at the models now. If you remember, we have defined active residues on the antibody side. So these are the red one. We have defined active residues on the antigen side. These are the orange one, this is visualization. And we have defined passive residues, the surface neighbors. And you see that pretty much all of the residues, at least the active ones, they are at the interface and they are making contact. The passive ones, like these guys here, they are not at the interface, but it doesn't matter, they are passive, okay. Since we are optimizing against this contact, these distances, those should be at the interface at the end of the docking. If they are not, then something went wrong, or maybe your data were not very good. So yes, you are at the interface, but you cannot use that as a validation of your model because you are optimizing against the data. You can say, yes, the model validates, it satisfies the data, but there might be more models that satisfy the data. It could well be that another cluster, and if we were to visualize other clusters, it's in the command line practical, you might see that the cluster which is 10 angstrom away is using the same interface, but it's a 180 rotated solution. So it will also satisfy the data most likely, but it's the wrong solution, and if you look at the energetic in that case, it's actually worse. So just satisfying the data might not ensure you, yes, your model should satisfy the data, but it's not a proof that the model is correct. If your optimization technique is very efficient, then it should satisfy the data. But again, it's not a proof that the model is correct. Now, how good is it? We can superimpose this on the reference structure. If you're interested how the code looks like, there's a Python code hidden there. And now you see here in which one is which. I think it's, doesn't matter. Oh, model 1, model 2. So red and orange, I think, is the crystal structure, and blue and green will be the model that we generate. It doesn't matter who is who. And you won't see the backbone. So you see there are small differences. You see here the loop is not exact, but in general, that's a very nice solution, and you said that you get the RMSD of those as well. So all is good. So if you manage to get to that point, then congratulations. If it's still running, then you have to wait. There are a number of bonus things. So are there questions on this? Was it clear? Yes?
You said the models may fit the data, but may not the right ones, right? Like the interface residues that we have found here.
Yeah.
But how far can we take this to the next step, like for the modulating those interface region? If my protein has no experimental structure.
Yep.
So based on this one, can I proceed with the next step for modulating the hotspot residues in the interface region?
So, well, the next step will be what will be your next step?
I need to design a small molecule that interrupts this interaction.
So that's, you know, if you have nothing else, you might have to trust. If your best cluster is much better than all the other clusters, then you can put your money on that one and hope that you can move forward, but you have no guarantee.
Oh.
That's you know, that's it's science. If I was to do, you know, I would run other methods as well. You might try other docking methods. There are several, like ClusPro, there are more methods. You can run AlphaFold. Maybe if you start seeing the same solutions coming out of multiple methods, then you have more trust in those. That will be one thing to do. So I would say, no, don't put your money only on one. But and the other thing is, if you have a model and you trust it, and maybe before you spend a lot of time and effort and money in designing small molecules, it might be good to test the model, because your model might tell you, if I mutate this residue, maybe I'm going to kill the interaction. So you could do an experiment, and there are a lot of good papers being published, you know, in top journals where people are building on modeling, but then they do a bit of experimental work to actually prove that the model is correct. And if you can do that, then you can trust, you can go on. You can, you know, what you also see people doing, so okay, I'm going to run molecular dynamics on those models. And you run 100 or 200 nanoseconds, the model might be perfectly happy, but 100 or 200 nanoseconds is a very short time. Yeah. Okay, the dissociation might take much longer. So again, 200 of stable MD doesn't tell you that the model is correct, it can still be wrong. So yes. It's life. The other thing that I would say, okay, if you have data that you did not use in the modeling, so that will be not like, you know, when you do machine learning, you have a test set that you never use in a training. So if you have some data that you did not use in the modeling, does your model explain those data? That will be also something nice to do. Or you might have mutations that are known. If you're looking at an interesting system, you know, maybe cancer related or whatever, there are mutations there that are known to affect the interactions. So can you explain those mutations based on the model with the mutation ID interface? So look at all the knowledge that you have on the system to try to find arguments to validate your model. But don't blindly take the first model and then start running with it. Yeah. And, but there is no magic bullet that gives you full certainty that this is the way to go.
Yes.
Yeah.
Okay, thank you.
We have done some, also we have published once a paper where we actually do MD on the models on different clusters. So when you have multiple clusters that have rather similar scores, And what we are monitoring, the energy of the system might be stable, but what we are monitoring are the differences. So how fast does my model move from its starting point? And if you think of it in energetic landscape, if you are a good model that will be somewhere in a minimum, you will say, okay, it's going to move, but it's not going to move far away from where it started. If you have a wrong model, it's more likely that it's going to move further away from what it was. Even if you're MD, then it moves away and then it's stable. But you see, so by monitoring basically the changes with respect to your starting point, you can use that also as an additional scoring. So that's, and you don't need to run long for that. So you don't need to run microseconds, because if it's not very good, it might move away very quickly from the start, not dissociate, but you disrupt the contact very quickly. So that could be another way of looking at that. Yeah. Yeah, so like 10, 20 nanoseconds and monitoring the changes in contact, for example. Are the contact changing very quickly, or they are going to change anyway because things are moving, but if you remain around it, so at least we had a test set, I think, of 8 complexes where we played that game, and that was kind of indicative, so we could have a very simple model to try to distinguish, especially in cases where you have multiple solutions that have similar scores where you don't know which one to select. If there's a clear winner, then you are in better shape. It might still be wrong, but at least you have a kind of a unique solution. But if they are all close to each other, then you have a problem. Yeah. Okay, so I don't see any urgent question anymore, and we still have a bit of time. Anyway, the party only starts at 6:30, I think, so we still have a bit of time. So I want to show you a few more things. Again, everything is online, so you can revisit things. Dissecting interface energetics. What is the impact of a single mutation? So you have a model and you want to select a residue to mutate, for example, or maybe you want to optimize your structure and start doing a bit of design. So this first bonus section is basically using HADDOCK to calculate the impact of mutations, and there is you could select. There are different things that you can do here. So you could use the alanine scanning module of HADDOCK to basically scan the interface automatically, and you see here a small workflow. So I have a structure. I create the topology. I do a short minimization. If the structure comes out of HADDOCK, maybe that will not even be needed, but we just do a short minimization, and then we do this alanine scanning. And in this case, we scan, it's alanine scanning, so we mutate every residue at the interface, so it automatically detects the interface, mutates everything to alanine. And, but you could specify that you have to mutate to other residues. So you can select what you want to do and generate a plot of it. So you could run this workflow. Probably my still running there, so I'm not going to run that one, but just to show you. And what you get at the end of the workflow, these are pre-calculated. So there is again a text file that gives you for each amino acid that you mutate, and again they are selected automatically by HADDOCK from an analysis of the interface, and it's basically calculating the difference with respect to the original mutation. So you have, when you mutate, you will have positive difference and negative difference. And it also gives you, this should work, it gives you this plot, which has the change in score, which is the blue ones, so that's the HADDOCK score. It also shows you the change in van der Waals energy, the change in electrostatic energy, and the change in dissolution energies. And now you can start looking at a residue that have large changes. And the delta is wild type minus mutant. Okay? Wild type minus mutant. So is a positive score or a negative delta better? positive score is better. So positive score will mean that all scores are negative, okay? If the van der Waals energy electrostatic should be negative in principle, okay? The energy function that you use, the more negative, the better the energy in that case. So the more negative the value, the better is. So if you compare, so you take the score of the wild type minus the score of the mutant. So if the mutant is worse, that should give you a negative value. It means that the score of the wild type is lower than the score of the mutant, okay? And you take the difference, so that will give you a negative value. A positive value should be something that improves the binding. Okay, so the positive are the ones that might potentially do something to the interface, improve things. The large negative ones are the ones that are very important for the wild type interaction. Okay, this is the way that you can look at this. Yeah, so say I have a score of, my wild type has a score of minus 200. Okay, I do the mutation, I guess a mutant which has a score of minus 150. So the score went up, okay? When I take the delta score, I take minus 200 minus 150, that gives you minus 50, okay? So that means that the mutant was better than the alanine scanning, and you say, okay, that residue in my wild type sequence is important because it has a large negative delta when I do this scanning. So the negative ones are the ones that are in the current structure, wild type sequence, have a strong contribution to the binding because they have a strong change in score. If you do your mutations and you have, say, minus 200, and then you do a mutation and you get minus 250. So the score has become better, so it's lower. The difference now, it's minus 200 minus 250 gives you plus 50. And that means that positive value in this plot are giving you mutations that will improve the binding if our energetic is correct. Again, these are not free energies, okay? If you want to test that, you should do free energy calculation and molecular dynamics. But this is gave you a first handle of which residues have important contribution. We have seen, for example, what was it? There was an arginine, if you remember the chord plot, there was an arginine that was making a lot of contact. So I will expect that this guy must belong to the negative one. There is an arginine here, I don't know if that's the one I was looking at. There's a lysine here, which has a strong also negative. Here there is another lysine. It has a positive van der Waals, but it has a negative electrostatic. This one is also interesting. And you can look based on van der Waals or score or the different components. So these are also aspartate, so these are all quite important. Here there's a tyrosine, which is also important. Another tyrosine here. The HADDOCK score is the blue one, so the large blue one are the ones that are interesting. So you can see, and there are a few where we get a positive score, but not that many. So this serine here, 32, if we mutate it to alanine, positively interesting. So at least this, if you want to propose a mutation, you want probably mutate a residue that has a very strong contribution to the binding, and this will be a way of very easily identifying those, because you get basically a score per residue or delta score per residue. And you don't need to do, so HADDOCK is doing the mutations for you, okay, basically. And the way it mutates the residue is simply by changing the name of the amino acid. And then when we run TOPO-AA, it's going to regenerate the side chain if it's missing. So you don't have to manually do the mutation. You can, of course, but it's not needed. So you see, for example, so the one which has the most negative contribution is aspartate 58 in the delta score on chain A, and lysine 97 in chain B. And the one that might possibly destabilize a little bit the interface is serine 32 and lysine 47. So we can look where is 58 located. So, whoops. Ooh. And then you can look at what is it doing. You see that, for example, it has an interaction with a lysine side chain here. So maybe it's better depicted here. So this 58, if you look into model, makes actually 2 salt bridges with 2 lysines. So it's in between 2 lysines, making a very strong salt bridge. So if you want to kill the complex, you know, if you mutate this residue to a positively charged one, most likely it's not going to bind anymore. So that's the other one is a scoring scenario. So here, if you have a set of models, so that's what we're using, for example, to score complexes in Capri. So we did modeling of this complex with AlphaFold 2 and 3. So this is the scoring scenario again. So there are the AlphaFold predictions here. There's AlphaFold 2 prediction, AlphaFold 3 prediction, and then a set of structure that were obtained with HADDOCK. And then we have a very simple scoring workflow. So we do topo A, EM scoring, and then we cluster things to have a cluster-based scoring at the end. And then you can run the full workflow, and then you can see what they are. And actually, you can also look which one was which. And actually, you see that the scoring works very well in this case. The best model, again, we know the reference here, are close to the answer, while the wrong model goes down. And if you look where are the AlphaFold models, they're very down. And then we're not going to spend much more time on this, but I just want to show you one more thing. So alanine scanning was doing this systematic scanning. But if you want to do everything against everything, there are also tools out there that you can use. There are machine learning models, basically, that are predicting what are mutations. There's Foldix, maybe you have heard of those. Proton is one of those. There's a pre-calculated I think I have the wrong link. Online server. Here, pre-calculated is here. Yes, go there. So that's a server which is in Izmir, Turkey, which is basically doing a systematic mutation of each amino acid at the interface of a complex versus each amino acid, and it's using Foldix and related things. It's a bit slow. And you get a matrix, a heat map matrix of which mutations might be interesting. And then you could select some of those mutations and then test using a HADDOCK score to see if they are better or not. So it seems to have a bit of a problem. And the most enriching mutation it's proposing is, again, this is serine 32. It was showing, alanine scanning as one residue that has not maybe destabilizing a bit the complex. And it proposed to mutate this one to a tryptophan, which might seem strange because you put a very large aromatic side chain at the interface. But actually, if you do the mutation and you calculate the scores, so you see here that's a command that edits the tryptophan of a serine 150 in the PDB file to tryptophan. And then we run HADDOCK scoring. I'm just going to run that one, and then I stop. So this is the reference complex. So this is the crystal structure that we are taking. So the first line create a mutation where we change serine 150 to tryptophan, and we just change the name. So the side chain is not there, but HADDOCK rebuilds it. The second line scores the crystal structure, the native sequence. And the third line scores the mutant that we just created. And you see the HADDOCK score, minus 147 for the native, and now the mutant is minus 167. If we were to take the delta score, that will give us a positive value of 20, plus 20. So that seems a stabilizing mutation, which seems strange. You mutate a small amino acid to something large. But actually, if you look at it, it fits quite nicely in the interface, so it's not clashing. And what I personally like also about this mutation is that this aromatic tryptophan side chain is now stacking against the aromatic tyrosine side chain. So somewhere it makes sense. So HADDOCK is giving you a nice score, and Proton, which does this systematic thing, is also identifying that. You know, so if you want to skip the reception tonight, you say, no, I don't want to eat and drink, I want to work. So, you know, the challenge will be find mutations that beat the minus 167. It's probably hard. Okay. On the other fun challenge is find a mutation that gives you the worst score as possible. That's also fun. Okay, so then you want to look at residues that, well, aspartate 58, we looked at it before in the middle of two lysines. Let's put an arginine there in the middle, or lysine. Probably that's going to do bad things, okay? So, you know, these tools are there to do many things. So it's not only about docking, but you can also use, if you have a model from somewhere, or if you have models from molecular dynamics and you want to go this analysis, and so you can do a lot of things. So they are very useful for many purposes, and also for refining, for example, AlphaFold models and get some of the energetics, because AlphaFold doesn't give you the energetics of your interfaces, but that will be a way of getting the energetics out. So combining the two basically is the message here. Okay.